Carbon. Our bones and bodies would not exist without it. Nor would plants or microbes, or the incredible carbon chemistry that links us all together. Carbon is the stuff of life on Earth. And it is old. Carbon was forged in the nuclear furnaces of long-dead stars before our solar system was even a wink in the celestial eye. This means every atom now on Earth has been on a restless adventure since the dawn of time. And that as far as carbon is concerned, every life form on the planet, us included, is 100% recycled and recyclable. Right now, about 1 trillion tons of carbon are bound up in living organisms. But far more is locked away in the fossil fuels like coal, oil and gas, and in the very rocks of the Earth, deep underground. Of course, the carbon in you and I, and the air we breathe, is older than the Earth itself. But we can start this story of carbon, the crude story, in the fiery mouth of an active volcano much like this one, on a very different looking planet, a long, long time ago. Back in the mid-Jurassic, the Earth was a dinosaur-inhabited world on the move. The continents, once joined together, were now breaking up, and the sustained volcanism pumped massive amounts of carbon into the atmosphere. Enter our central character, a single atom of carbon. It's been pumped out as a carbon dioxide molecule, joined at the hip to 2 oxygen atoms. It may be just one in a swarm of countless zillions, but it's as good a guide as any to take us through this oily adventure. As a gas, carbon dioxide helps set the global thermostat in the comfortable range. Too little carbon dioxide in the atmosphere and the entire planet will freeze. Too much and it will cook all over. And the Jurassic Earth is cooking. Hugh Jenkins is an Oxford University geologist. He spends a lot of his time with his head back in the Jurassic, trying to fathom where all the carbon was going and what the world was like all those years ago.
Well, I guess for half the globe would have been blue, studded with clouds, and the other half would have been brown and green.
From orbit, you would have seen the continents bunched together on one side of the planet, with the land to the north and south separated by a warm, ancient ocean called the Tethys. There were plenty of clouds, but no great ice caps at the poles.
As far as we know, there was no substantial ice on the planet, so it would have been a warm, what we call a greenhouse world with elevated levels of carbon dioxide. Imagine, if you will, a sort of gigantic Bahamas extending right over large tracts of what we call today the Middle East. That part of the world, you'd have a lot of shallow water, carbonate environments, so not so different from the barrier reef. Obviously, there are the marine reptiles, and there are the land-loving reptiles as well.
It was into this greenhouse world that our carbon atom had been released. Now it was one of the many CO2 molecules helping to keep the climate of the dinosaurs hotter than any other period in the planet's history. For perhaps 100 years, it swirled through the landscape, over oceans and deserts, mountains and lakes. Eventually, it drifted into a primeval Jurassic forest. It spent a season inside the leaf of a ginkgo tree, and another 50 years in the body of the dinosaur that ate it. It passed from plant eater to meat eater, before being exhaled back into the atmosphere, once again as carbon dioxide. Our molecule drifts on, and finally is swept out over the ancient Tethys Ocean. One day in the future, this warm equatorial seascape will become the oil-rich deserts of the Middle East. But now, the sea is rising, and so are the temperatures. Both the atmosphere and the oceans are loaded with CO2. Our molecule slips into the sea to become food for a phytoplankton cell. Trillions of these tiny plants swarm near the surface, all soaking up the sun and sucking in CO2. Inside this cell, our carbon dioxide molecule is transformed into an energy-rich sugar via the flash of a prehistoric sunbeam. As a means of capturing solar energy and storing it for later use, photosynthesis is brilliant. The cell divides, and then divides again. Sunlight and carbon dioxide are being harvested and squirreled away into organic cell walls and fatty carbohydrate molecules. The whole Tethys Ocean is blooming with phytoplankton. Jump forwards to our modern world. The individual algal cells in a phytoplankton bloom may be microscopic, but en masse, you can see them from space. Giant green swirls appear in places where plant food is concentrated by winds, currents or rivers, or trapped by restricted circulation. Our carbon atom, bound up inside its dead planktonic host, settled into the stagnant darkness, along with billions and trillions of other little hydrocarbon-rich corpses.
The oceans then were just replete with organic matter. These microscopic plants proliferated in quantities that the world hasn't seen for millions of years. And they were also able to be preserved because these oceans were very prone to stagnation. So there was much less oxygen in the water, much less overturning of the water. The organic matter would sink to the bottom and be preserved, and then it would be buried by rapidly accumulating sediments.
To drive out the oil, it needs to be cooked slowly in the moderate oven of the Earth's oil kitchen. And to enter the kitchen, the rock needs to be buried deep underground.
When it gets to a certain depth of burial, some thousands of feet below the surface, it's physically cooked by the pressures and the temperatures you get there, and the organic carbon cracks and goes from this original material to light sweet crude, as oil people tend to call it.
The temperature is critical. Bury the shale too far down and it is overcooked into natural gas. Too shallow, and you end up with a half-baked greasy oil shale. Deep below Saudi Arabia, the conditions were just right, like a hot pot of tea for millions of years. Light, sweet crude containing our carbon atom began to flow like warm honey from the buried source rock. Of course, the Earth did not stay still while all this happened. The continents continued to break up, and nor would plants or microbes. 3 times during the reign of the dinosaurs, once in the Jurassic and twice later in the Cretaceous, thick black shales were laid down in the Middle East. So much that 2/3 of the world's oil comes from organic sediments buried here alone.
In Saudi Arabia and Kuwait and the 5 main Middle Eastern states, there were really singular conditions. You had a number of things that absolutely are required for giant oil fields. Really rich source rocks from which the carbon can be cooked at the right temperatures and pressures underground. Really excellent reservoir rocks where the oil can migrate through the microscopic pores and be trapped in these reservoirs. Really good so-called cap rocks. These are the impervious rocks over the reservoir rock that actually locks the oil in place.
Did you see the white color here?
Yes. And finally, really gentle structures, folded structures, anticlines, geologists call them, in which the oil could sit. Most people don't realize this. They think you can find oil anywhere. The vast majority of the planet is actually devoid of oil because these special conditions are not met.
Against these odds, the crude containing our carbon atom seeped ever upwards. It oozed slowly through the most porous and permeable rocks available, like ink in blotting paper. Eventually it could go no further, and trickled into the limestone pore spaces of the largest oil reservoir on Earth. And there it stayed, trapped until humans came along. The sludgy remains of tiny, brainless plants waiting to hold dramatic sway on the future of the most intelligent life form the planet has ever seen.